We should start. So, good morning, good afternoon, or good evening to everybody joining us from around the world. And thank you for being here today. I'm Mary Salvana, Assistant Professor in the Department of Statistics at the University of Connecticut. On behalf of the organizing team, I'm pleased to welcome you to the Spatiotemporal Statistics and Data Science online seminar series. This series brings together professors, researchers, practitioners, and students worldwide to explore methods, theory, and applications of spacetime data. Our goal is to provide an avenue to share ideas and to spark conversations that push the field forward. We're grateful for the support of the ASA Section on Statistics and the Environment, ENVR, the Royal Statistical Society's Environmental Statistics Section, and the International Environmetric Society, or TIES, whose communities help broaden the reach and impact of this series. Each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We will collect them and raise them after the presentation. All talks are recorded, and the recordings, along with the slides, will be posted on our website. We typically host 1 to 2 seminars each month, and you're also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you'll find those details as well as other resources at stsds.org. With that, I'll turn it over to my fellow organizer, Yan Gong, to introduce today's speaker.
Hello, everyone. My name is Yan. I'm currently a visiting assistant professor of statistics and data science at Mohammed bin Zayed University of Artificial Intelligence in Abu Dhabi and the co-organizer of this STSDI seminar series. It's my pleasure to introduce today's speaker, Dr. Tanujit Chakraborty. Dr. Tanujit Chakraborty is Associate Professor of Statistics and Data Science at Sorbonne University, Abu Dhabi, UAE, and Sorbonne Center for Artificial Intelligence, Paris, in France. He is also an adjunct associate professor at NUS Singapore. He earned his habilitation in mathematics from Sorbonne University, Paris, and a PhD in statistical AI from the Indian Statistical Institute, ISI, Kolkata. His work integrates statistical learning, graph theory, and deep learning, with an emphasis on developing models that can reason about structured and temporal data. And with that, I'm very happy to turn it over to Tanujit to begin his talk.
Thank you so much, Ian and Mary, for inviting me. Although it's an online talk, so I'll try to explain almost as possible like I can. So today's topic is space-time extremes and geometric deep learning. So my background is in statistics, but I mostly worked on machine learning topics during my PhD, and even nowadays I'm continuing working on deep learning. So that's why I'll be starting with introducing few things and probably some of the things that are very commonly used nowadays in geometric deep learning research area. And this talk is all about how do we connect all these things. So you will, at the end, you will find all of them to be connected in solving a real world problem. I'd like to start with a very popular say by Swami Vivekananda. He's one of the very famous Indian person who went to US and gave his talk at various places about spirituality and other stuff. He talked about space-time, this particular thing, that space-time causation, or what he said, name and form, is what is called Maya. So Maya is like illusion, okay? So time, space, and causation are the three conditions through which our mind actually perceives. So I hope that after this talk, you will be able to connect all these things together. So before entering the actual talk, I would like to introduce few background stuff just for the sake of broader audience. So when we introduce time series is introduced as a set of observations. When each of the observations are recorded at a specific time, for the time being, I'm talking about regular interval time series, which is where the phenomena is observed at a regular time intervals. And By forecasting, we always try to understand how this sequence of observation will behave in future. I'm giving some loose definitions. And then we have, when we have data in both space and time, like when we have data which are captured on various observations, when the observations are captured at different time, also at different locations, we call it spatiotemporal data. For example, we can take the example of air quality data. Let's say we have different sensors located in different places of Abu Dhabi, and then that collects data over a period of time. That's a simple example of a spatiotemporal data. Now, spatiotemporal data can be of grid type. So when we have grid type of data, let's say we collect a video. Video is also another space-time data where the data comes as an image. So it's treated as a grid. Now that data can also be another form which is called graph structured data. By graph structured data, I mean when we have sensor networks or traffic flow data or social interaction data, where we can observe the data as a graph structure. So when all the observations are collected, they will have the complex relationship in both space and time, but we can represent them using a nice graph structure. Now, talking about graph structured data, a lot of real world data doesn't live on grids because deep learning become very popular as a tool for particularly handling grid data. But there are a lot of observations which doesn't really live on these grids. For example, if we have a social network in which we have different connections, let's say we assume the network of your Facebook network. So you are connected with some of the people, they are connected with also some of the other people. So this sort of networks, they are graph structured data. There are multiple other structured graph structured data, could be molecule data, could be protein interaction data, could be road network data or metro data. And this sort of data for which particularly model that have been developed for grid structure like CNN, RNN structure or sequential structure, they do not necessarily work directly. So how do we build those models for these data sets remain a challenging problem in deep learning community. Now, before getting into details of how these graph structured data look like and for our problem, I would like to define what is called a graph just for giving the notions. So graph represents the relations between a collection of entities. So those relations are represented by edges and those entities, we call it nodes. And based on that, there could be some weights that are defined throughout that. So mathematically, we can represent the nodes by V. E is referred as edges, which is the link node pairs, and the weights that are associated with the edges. How do they look like? They do look like something like this. So we have the nodes, which is represented by 1, 2, 3, 4, 5, and we represent their connections out there, and there are certain weights that could be the distances, let's say. And we represent an adjacency matrix, which gives particularly the element of the adjacency matrix will be nothing but the pair of nodes that are adjacent or not in the graph. So if they are adjacent, I can take their weights to be put inside the adjacency matrix, and this is a particular graph which is a very static graph. Now, in case of space-time data, we do not have a static graph. We have a dynamic graph. Now, how do we represent that dynamic graph? So a dynamic graph is a graph whose structure and or associated properties, they change over a period of time. What do we mean by that? We mean by that one sort of graph, dynamic graph, is spatiotemporal graph. Spatiotemporal graph is a sort of graph where the topology remain fixed. So the connections and the nodes, they remain fixed. But the feature that we observe that change over a period of time. By feature in statistics, what do we mean by attributes? So that attribute will change over a period of time. Let's imagine the temperature. So the locations remain same. There is no new things are happening. Let's say no new construction, nothing is happening. The locations remain same where we observe where we have the sensor to measure the rainfall or AQI, air quality indices. And then their values changes over a period of time. So that's an example of a spatiotemporal graph. Now there could be some very difficult sort of representation of spatiotemporal graph, just like discrete time dynamic graph, where not only the attribute value changes, but also the vertices and edges, they also changes over a period of time. So just like you can imagine the collaboration network, during our PhD, we have been publishing, let's say, number of papers is my XT in every month or every year, let's say. And the people with whom we have been publishing paper during PhD would have been our supervisor or co-supervisor. And then we move to postdoc, we publish papers with different people, and we become faculty. We don't no longer publish papers with only our supervisors, but publish more papers with our students. So that's sort of a graph which can give you some idea about discrete time dynamic graph. Then we have another sort of graph which is called continuous time dynamic graph, which is a very much more generalized form. And there could be protein-protein interactions, and these sort of graphs are actually observed in biology, medical health, and all these set cases where you observe them, and the graph is observed individually with its timestamp. So we observe in certain continuous time space. So now, given this background, how do we design a machine learning model for this sort of data? I'll start with giving example with static data so that it becomes easy. Let's say we have a graph here which represents some connections, and let's say those are different individuals, and if they know each other, I put them as 1. If they do not know, I don't put any connections. It becomes 0 in the adjacency matrix. So given this graph, and let's say how many messages this share, let's say that's some observations we observe, that's a feature matrix. So we can concatenate. Concatenating is a very popular concept in deep learning, where we put them together. Let's say the way we do it, multiple linear regression setup, we put the inputs together and we concatenate with one vector in case of, so that we can get the estimates of beta naught. So very similar concept here. You take the adjacency matrix, you take the feature value, and then you put them together and train a neural network. But that has a lot of problems. One problem is there will be a huge number of parameters. It's a well defined, fully connected deep neural network to be trained. And if certain things changes in the graph, let's say if the graphs become temporally dependent, then you have to run that every bit and then. So every time, at every time point, you have to train a different network. So that's where it becomes complicated. So we have a problem that we have certain neural network that can be trained on a static graph or a dynamic graph also, but that will require you to retrain the graph every single time, retrain the network every single time. And we do not have anything that will be sharing the weights among each other, because the neighborhood regions, they will have impact on the air quality, on the temperature of nearest regions, or the disease incidence, let's say. So we need something that gives us weight sharing and handles this sort of problem. And there comes some solutions that was proposed since 2005. They are called deep learning on graphs or graph neural network structures. Now, I'll give you some brief idea about graph neural network, but then I'll again get into details of that when we will be talking about what methodology we designed. So given a graph structure where I'm given with an adjacency matrix and the feature matrix, we can design a graph in and graph out structure. So you can see the input is itself a graph and the output is itself a graph. In the hidden layer, we follow some idea of neural message passing. I'll explain that in a few slides. So that passes the messages between the pair of nodes and agglomerate. So you see, whatever regions are next to each other, they will be passaging the messages, because this idea comes from natural language processing, where people have been working with NLP problems, where people talk about text data. So in text, we see that let's say I got selected or one of my paper got accepted. The first thing I'll do, I'll message my collaborator, I'll message my friends. So that's what the idea of neural message passaging comes into picture. So those nodes that are connected to each other, that will pass the information among each others. And these passing messages between nodes will redefine the graph structure, and that will update the presentation. And those representations are updated through different hidden layers. I'll talk about that again in in my method, when I'll be talking about the method we designed. So then I'll explain it into much detail. So for now, it's a graph in, graph out structure where the hidden layer actually passes the information through neural message processing that this node is connected to this nodes and this node is connected to this node. This is the strength of their nodes, and you pass those messages inside so that you get a new embedded graph which is represented by Z. This paper became popular in 2005 to 2017. A lot of paper came during in this field, particularly for classification problem, regression problem, and IID data problem. Then after 2017, people started working on space-time data for graph neural networks. So here I give you a brief history of how these methods have been developed. So there are multiple spatial methods, spectral methods, and graph extensions that have been developed in this area on graph neural net. So the original paper comes from Gori et al., which was published in 2005. And very recently, there are a lot of papers. I just give you the papers prior to spatiotemporal domain applications. So these are papers that came before that. And then after 2017-18, then there are people coming in space-time graph neural networks area. Now, to give you much more broader context, so GNN become much more popular with this sort of applications, particularly DeepMind. They used graph neural network to reduce the travel time estimates. By the accuracy got improved much further for Google Maps using graph neural network. And graph neural network was used to discover powerful antibiotics using AI. And food delivery apps like Uber Eats, they use GNN based recommendations. And Chinese Academy of Sciences people, they used STGCN, that is spatiotemporal graph neural network, for forecasting their precipitation, which got published in GRL. Now, today's talk is specifically, given all this context, now I'm getting into the topic of today's talk. Today I'll be presenting a method that we recently developed. It's called Extreme Spatiotemporal Graph Convolutional Network for air quality forecasting. So I'll be trying to combine space-time data that consists of extremes and to solve that problem of air quality forecasting by designing something that combined extreme value theory with spatiotemporal graph network, neural networks for air quality forecasting. So that is going to be my today's talk. I'd like to thank my co-authors, Madhurima, Anubhav, Saudip. They are from Sorbonne, I am Bangalore, and also SAPSI in Switzerland. This paper has just now published in JRSSA. Now, coming to a nice, interesting problem with which we started working on. So this was a government supported project in which we were given our data of Delhi's air quality. Now, why Delhi? So if you look at the chart of most polluted cities in the world, so Delhi in 2023-24, it used to rank at the top, which is not a good sign, but its air quality is massively bad. And this is particularly because Delhi is a landlocked city. So you can see, if you see in the map of India, it's in the middle of India and it's landlocked. There are lot of things happens around Delhi, like in Punjab and other places. People burn their stuffs and all those pollutions come inside Delhi. It is particularly very problematic during winter season, particularly. And this is because of the fact that there are a lot of issues with the particulate matter and harmful gases in the air of Delhi. And industrialization is also another factor that contributes to Delhi's rising air pollution. So to understand air pollution, there is National Ambient Air Quality Standard, which gives you certain threshold based on different regions. If your air quality metric for that particular region crosses that threshold, we call that place to be polluted. Delhi has put a lot of efforts, but still remained that. And we got this project to come up with some method that can give them better idea about what will be the future forecast of Delhi's air quality, what will be the forecast of that. And that will help them in decision making, because the kind of model they have been using, they are very old school models, and particularly they have been using for STARMA model, which is spatiotemporal ARMA based models, which couldn't really capture the extreme observations and generating like average forecast after certain points. So now let me give you how the sensors are plotted in Delhi and how Delhi's data look like. Now this is how Delhi looks like. So these green stars, they represent the different locations of Delhi where the sensors are plotted. And this is the capital of India. So they have lot of sensors installed that in that place, and there are total 40 sensor locations, and at every location they got data for every minute. So all this data being recorded, and then we got this data from Central Pollution Central Board, which is Delhi's governing body, and they have all this data with them, and those sensor locations gives us hourly data of concentration levels of all the major air pollutants, PM10, PM2.5, NO2, SO2, all these variables. So if we can come up with a nice model that can tell Delhi, okay, Delhi government that, okay, I can tell you for next 6 months how the air quality will look like during this period and during that period. So that will help them to come up with a better strategy to mitigate this issue. Now, let me show you how this data look like. By the way, for those who are not aware of, PM10 and PM2.5 are meaning that particles that are 2.5 micron or less in diameter. So it's based on those particles, and those are the most harmful particles out there that causes the air pollution. So Delhi's air quality data we had till 2019 to 2023 data. And if I present the data on a daily basis, this is how the data look like. So the data look like the following. If you see, the NAC threshold for PM 2.5 is 60 microgram per cubic meter air. Whereas if you see, look at the plot on the left side, the PM 2.5 for most of the test stations around the world crosses many a times 100, 200, even 600 sometimes. So that's what reflect that Delhi's data is having lot of issues with the air pollution. Delhi is particularly having. This is also true for PM10. For PM10, the NAC threshold is 100 micrograms per cubic meter, whereas it goes beyond 600, 500, particularly during the winter time. For NO2, it's relatively better. So what kind of statistical properties we find out of in this data? We saw that most of these data sets are nonlinear in nature. They are non-stationary, which is very trivial for air quality data. There is a long-term dependency, which is also true because of the fact that in Delhi, particularly there is a seasonal component that particularly in winter season, you will see a lot of the ground observations are actually beyond the threshold always during the winter and pre-winter and post-winter also, that emphasis comes. And there is a seasonality factor which is very common in air quality data. Another thing we observe that is not usually observed, which are called extreme events. We can see a lot of extremes are coming here. So there is a good reason to create something that will be sort of tackling those extreme values for the air quality data of Delhi. Now, when talking about extremes, we studied probability 101. So we know that for a stochastic process, we understand their average behavior using center limit theorem. Whereas when we have extremes in the data, we can model those rare events using extreme value theory. Particularly, two promising methods are there. One method is called block maxima method. So just like for Delhi's data, I present here in a particular location called Alipur, Delhi, the PM 2.5 level. This is the daily data. For every month, I put the data as a bar here, dotted bar. So if you can see, if you take this method into consideration, the block maxima that we see in one particular block, that is not going to be a block maxima for the another block. So that's why we thought, okay, block maxima is not really working for this sort of data. So we take recourse to peaks over the threshold method. Now in peaks over the threshold, the critical thing is to find out the threshold. A lot of work have been done in statistics for that. But for this sort of problem, we are already given with the NAC threshold. So whatever value that goes beyond that threshold, we can model those exceedances using generalized Pareto distribution. And those threshold is given based on the NAC threshold for Delhi. So here from we got some idea that, okay, with Delhi's data, if we have to build a probability model, let's model it using GPT. So let's do that. So we are given with the data. Let me take the data of that denoted region that is called Alipur's data. If I plot the data and if I just take the extremes and I feed the model, GPT model, generalized Pareto distribution, would be seeing that, okay, it gives a very nice fit. So peaks over threshold approach really work on the exceedances. That's a nice phenomena that we observed for this data when we started studying this. And in Delhi, particularly, you can, if we ask that why this particular thing happened, because in winter, not only because of the landlocked thing, but there pre-winter, there are certain festivals in India, particularly Diwali, if you are aware of. During that time, a lot of air quality issues happens also. And also there are low temperature issues. So altogether, that contribute to the extreme measurements arising in that particular time. So the next questions come in our mind that how can we really accurately forecast AQIs for Delhi in the presence of these extremes? Will be not, our job here is not to find out like the change point. It's not just telling out, okay, this is the time the extremes is happening and how they look like. In our forecast, if we let's say take a forecast of next 3 months, will I be able to get those points that now, okay, you see the peaks are coming here and there. So the forecast will also include those extremes. That was our kind of job for this project. Now let me come to the solution that we started designing. We call it extreme spatiotemporal graph convolution network. It combines two different approaches. One is extreme value theory, another is spatiotemporal graph neural network. And there we build a model that can incorporate the peaks over the threshold idea that we use for the exceedances, plus the idea with which we can model any spatiotemporal time series data using graph neural network, so that it can be robust to the extremes when generating the forecast. So ESTGCN is something that will better optimize the model parameter to accurately forecast in the presence of multiple peaks, and it will be able to capture those peaks in the future. Now, before getting into the model, as I told you, I'll again come back to GNN and try to tell you what is this neural message passaging idea for spatiotemporal data. So GNNs, as I discussed earlier, they are optimizable transformation of all attributes on the graph, and that will preserve the graph symmetry. So the graph structure will be preserved, only it's an embedding. That embedding is done throughout different hidden layer. In every hidden layer, there are different multi-layer perceptron or graph convolution networks. They are working. Now, how they are working? They are working through a mechanism called neural message passaging. Now, how this neural message passaging idea look like? So neural message passaging works to exchange the information among the neighborhood nodes. So, and the neighborhood information that is going to impact another locations, that will be embedded within the temporal information. So how it actually works, let me present it using a picture, then it will be easy. So let's say we have different location A, B, C, D, E, and we know the connectivity between these locations. Let's say we are interested about traffic forecasting problem. So let's say this particular location gets impacted from the traffic of all these locations. So we collect all their data. Let's say we have the first bar diagram represent the temporal observations of the highlighted yellow colored box, and then the other boxes that are connected with that. So we have all these informations. So we try to aggregate those informations from the adjacency nodes. How the aggregation looks like, you see, we create a concatenated version of this thing and create an aggregated information from the adjacency nodes. Now this aggregated information passed through a transformation by neural network. How does transformation look like? So this transformation could be a multi-layer perceptron architecture. You can imagine for now any nonlinear model. So any nonlinear model that will be incorporated there to pass this information so that we can come up with a better version, embedded version of the graph that consists of the impact of the nearest locations that are connected with the location for which we are trying to understand, and that will be done over different hidden layers. So that's why we call it a graph in graph out structure through neural message passing. So there will be an updated function with new information. So given a graph, you will be getting finally another graph with the space-time information inside it. So the first information, you have a multivariate series without the impact of the emphasis of the neighborhood locations. Now, given you have the adjacency matrix and the multivariate time series, you can combine them and come up with a ZT, let's say ZTI, which will be an embedded transformed series from the given graph based structure, spatiotemporally structured data. Now, once you have the new structure transform graph, you can use them for anything. You can use them for classification, regression, based on different problem, for forecasting. All this problem you can study. For forecasting, the first paper appeared actually a lot later. Actually, the first very popular paper become spatiotemporal graph convolutional neural network, which got published in a very popular conference ICHKAI in 2018. And that is kind of the first paper that everyone cites in this particular domain. So graph in graph out structure, and throughout the different layers you make a transform graph which gives you the impact of the connected regions and their impact through a neural message passing idea. So that's what gives me the idea of graph convolutional network for spatiotemporal data. And this sort of graphs can be used later on for imputation, for forecasting, for node classification, for edge classification. For all these problems we can use them. And if we use a simple multi-layer perceptron, we call it graph neural network. If we use convolutional neural network for the finding out the hidden layer, then we call it graph convolution networks. That's the basic difference between these two structures. Now, given enough background, now let me come to the structure that we designed that can combine the idea of extreme value theory with this graph neural network structure. So we are given with this data of Delhi's air quality. We have n locations. We have total time index data for total capital T number of timestamps. Our job is to come up with a model that will give me a Q step ahead forecast for all the locations and based on those T historical observations. So the way we thought of designing this model is we'll try to first develop the spatiotemporal graph with the nodes and the edges, because we know the connections which are neighborhood of the locations, so that the impact of the particular area can be understood. And because Delhi is a landlocked place and mostly Delhi doesn't have but too many rivers and also too many mountains actually, so that's why the connectivity graph is also very easy to find out. So we are given with this data xt and a, which is a is the adjacency matrix. Now, how do we compute the adjacency matrix for this sort of data? There is something called weighted Haversine distance, which is also called earth movers distance, to come to rescue. Earth movers distance is a particular method to compute distance on different locations on Earth. So it's on a sphere. You can compute based on the latitude, longitude of the sensor locations, and based on the Earth's radius, you can compute this distance. And then once this distance is computed, I can compute a kind of exponentiated version of minus dij square over sigma square, which will give me a normalized form of that distance so that I can use it inside my adjacency matrix. So given the data, given the information of air quality for, let's say, every day for 5 years, we can compute that matrix called xt matrix, and then A is computed based on Haversine distance based on the location and their distances using latitude, longitude, and Earth's radius. So once we have that, now I'll be creating a spatial module. How to this special module is created, I'll try to give an explanation using an image. So we'll try to here encode the structural and feature-based aspects of the GCN through a neural message processing layer. So the initial hidden, the first hidden layer will consist of, it's nothing but an initialization. So given the actual data, I'll try to initialize that value. So once that is initialized, I'll try to compute the next step, next hidden layer, which will try to combine the information of the neighborhood region through neural message processing. How that works, this is how pictorially we can see that. So that you can see on the screen that there is a circle, blue circle out there, that is connected with the 4 regions next to it. So how do we compute that value? So we first take the initial node feature, that is nothing but the at time point t for the location I, the exact value from the data. So initial node feature will be taken as an input. Then we collect all the neighborhood information. The neighborhood information means through neural message processing. So the neighborhood information that is also accumulated inside that structure as input, and we divide with by number of points that we are taking. So for this example, the ni is nothing but the number of points in ni is nothing but 4. And then we create a neural network. Instead of FTK, you can imagine any nonlinear time series model, nonlinear models particularly. And then that is parameterized through a multi-layer perceptron. So that gives me hidden layer 1. And we can keep on updating that over a period of time till the time we get the best sort of graph that finally have all the information extracted from the layer. For spatiotemporal graph convolution network, you do not need much layer to combine this information. Now, once you have that embedded version of the data, now instead of xti comma a, that information, everything we put together inside ZTI through a neural message processing layer. Now that will be passed through a neural network to finally find out the embedded version of the data. And that embedded version of the data doesn't only consist of the temporal information, but also it consists of the spatial pattern that is present in the data. Now, how do we create the temporal module? The temporal module now, given this is the spatial module that gives me output of a new embedded information that is represented by ZTI. Now the temporal module is built, we build it using LSTM structure. LSTM is a long short-term memory network which has also, other than input gate, a forget gate and output gate that solves certain issues that RNN had earlier with having no memory. Then we put some memory gate out here, and we can update those information, train that temporal. Now the embedded pattern will go through a temporal block and we'll be training that to generate the forecast. Now, when generating this forecast using this temporal model, we need to find out a right loss function. Now here comes a new loss function that we proposed for this work. The loss function that we created should have the idea of the EVT module, right? Initially, we trained for the exceedances some EVT structure, that is POT, based on POT approach, we designed GPD for that thing. Now, how can we integrate that inside this LSTM network? That was a big contribution for this paper. So we performed EVT on this data. We took the POT approach and then designed the generalized Pareto distribution on the data. We can write the conditional GPD for ith monitoring station with this particular probability function. And here I represent the shape parameter and the scale parameter also. Now here comes a nice idea that we thought of coming up with, is called POTL loss, which is defined like this. So POTL loss is nothing but the deviance or negative log likelihood loss from the GPD. So we feed the GPD, we compute for location I at time point t, let's say, we compute the negative log likelihood of the GPD. Now, why negative log likelihood? Because likelihood essentially measures how well a statistical model explains the observed data. Now, a negative likelihood is nothing but a deviance function, which is nothing but a loss function. So if we can get that loss function, so the lower the NLL, the better fitted the model will be. So it is like from the loss function perspective, we thought this will be a nice loss function that we need to minimize to get the better forecast for the extremes in the LSTM structure. Now, how that optimization is designed. So we build a new loss function that is based on two different things, which is the one thing is called data loss, another thing is called POT based loss. So data loss is the MSE loss, mean square error loss, when the threshold that is given by NAC will not be exceeded in the prediction, will only minimize the MSE loss. Once it exceeds, I'll not be focusing only on the MSE loss, I'll be giving more impact on the POTL loss. Because we learned that exceedances can be better model with POTL. So we create this POTL loss, which is nothing but the negative log likelihood. Because this loss we minimize. So this idea came to us from the idea of physics informed neural network, which actually is like a very promising idea nowadays to model some physical phenomena and also to solve differential equation. So there people uses a physical loss and also a data loss. So we thought of combining that idea for the sake of having solving this problem of extreme values in the forecasting setup, spatiotemporal forecasting setup. And this particular loss function, once we employ, we can see this has some nice properties. We studied some nice properties and we could see that we can simply use the gradient descent algorithm to find out the weights. And also we can estimate this beta 1, beta 2 through hyperparameter tuning, some k-fold cross validation, we can use it out here. So this particular modified loss function employed for handling the temporal dependency in the ESTGCN framework, and it from the Bayesian point of view, this works like a prior. So it's like POTL loss is a prior information that is going to the loss function. When it is minimizing, once it is beyond the threshold, you go far from the average values. So this is how the overall structure look like. So on the left side, you can see XTI, they represent the location and the data, time dependent data. And we have the adjacency matrix computed from the data. And on the data, we first feed a GPT distribution. From there, we use it to compute the loss function, which is incorporated when the threshold is exceeded. And we first apply a spatial layer where we get the spatial embedding. Then we do the temporal layer where we build a new loss function. We proposed a new loss function that combine the data loss with the POTL loss so that the forecast, they can be identified and they can be, once the threshold is exceeding, their values can be captured in the forecast also. Now comes the experimental setup. We have to experiment with multiple different uh, horizons, and we did a rolling window approach. We first thought of we'll be first forecasting 30 days test period, which is out of sample data, and then we started increasing it. We started with 60 days, 90 days, 180 days. Up to that we tried to do in our paper, and we report all these results inside the paper itself. So we compared with several benchmark model, because there are a lot of people here from KAUST. So there are people who worked on deep digging model, which has the probabilistic forecasting architectures for spatiotemporal data, but it's very less scalable because you do the concatenation in one vector. You use 1D convolutional network in that particular architecture. So this is not scalable, but our framework will be scalable and it can handle extreme values in your spatiotemporal data. Now, I give you a result for probabilistic forecasting with respect to CRPS. CRPS is continuous ranked probability score, which was proposed in JASA paper, very famous JASA paper in 2007. And if we see, this is a plot called MCB plot, multiple comparison with the best plot. So if we compare all the models that we tried to work for this data, the greens represent only the temporal model, multivariate temporal model. The blue represent all the state-of-the-art spatiotemporal model. There are STARMA, there are G-star, which you are all aware of. And we see that, okay, the rank of our model is far superior than many of the model, although it is very close to n bits and modified STGCN structure. And sometimes if you involve a multivariate array, might really works well also. Now we use for uncertainty quantification, because this is a STGCN is a non-parametric approach, and we do not have any nice way to get the probabilistic forecast here without relying on something that will be model agnostic approach. So we thought of incorporating the STGCN with conformal prediction, which is a model agnostic non-parametric method to generate the forecast intervals, prediction intervals for the data. It works like this. So we calculate the conformal score, which is based on the uncertainty model and the actual values. And once the conformal score is computed, we get the conformal quantile. And using the conformal quantile, we can come up with values that, okay, so this will be my bandwidth, yt hat plus minus qt hat yt hat u, where yt hat u is nothing but my uncertainty model. This is a very there is a nice paper on it. It's called Conformal Prediction for Time Series Data, ICML in 2021. So we combined this also with the STGCN so that it can generate the probabilistic forecast for the data. So how the forecast look like? I present here some of the examples from the paper. So this is particularly in February, which is the winter season, of course. And you can see many of the other model. I here put some of the other model like modified STGCN, which is a modified version of the 2018 paper for time series spatiotemporal air quality data. NBITS model, it's a neural basis multivariate time series model, which ranked top in kind of in our study from the temporal model point of view. If you can see the high peaks, they are mostly missed by majority of the model. Majority of the model cannot capture the peaks, but our model can still goes quite close to the peaks for most of these data points. So we got the figures for all the 40 locations for PM 2.5, PM 10, and NO2. Here I just give you for 3 different locations how they look like. And also the probabilistic band, you see they can capture mostly more than 80% of the points out there. So we also calculated the coverage score and everything else. So now I almost crossed the time, so I'll try to finish it up, wrap it up now. So the final highlight of this paper is to design something that has extreme value theory and deep learning together, and that solves a nice problem in spatiotemporal extremes. That is what we proposed STGCN. We applied it for 40 sensor locations. We got nice probabilistic bands. So we made a lot of stakeholders happy. And the future work is like there are a lot of work can be done, particularly if you are working in airborne diseases, other sort of data sets. You can integrate this type of framework. You can also this is a very flexible framework, so you can also integrate particularly temperature, humidity, all these variable inside it. We also build the structure in such a way. There are a lot of other applications of graph neural network for spatiotemporal data I would like to highlight here. So one application is spatiotemporal GNN for forecasting, but they are also used for imputation. So many of you have some problem with imputation also, where you have lack of data available because of sensor damage or some other things. You can also use this, our architecture, we didn't use it for imputation, but you can try to use it for imputation when you have spatiotemporal extremes in the data. And I'd like to end the talk with some open problems. So deep learning on graphs, they are very effective. There are a lot of nice applications happen. Particularly people used it for reasoning, multi-agent system, reinforcement learning system, where you can for car driving and other stuffs, and also for recommendation system. It is very much used for that. There are many open problems out there, particularly for theoretical statistics people. There are none of the theoretical results, not much have been done out there, particularly for classification setup to study the consistency result, rate of convergence, haven't been done much out there. And then in case of temporal setup, I haven't seen many papers which talks about asymptotic stationarity or geometric ergodicity of STGCN structures. Now, another sort of problem was there, which is can we build a generative model for uh, spatiotemporal data? There are multiple papers that came recently. We also presented a paper very recently, we submitted in a journal. And then learning on large and evolving data, particularly when the network changes. That's a very interesting problem. I give you example of collaboration network, right? And also in continuous cases, how do you see these things, continuous time series particularly? So that will be really interesting to work on. And another thing is, like, particularly if you are working on healthcare data, you will find nowadays most of the data are multimodal data. Even for mobile health, in which area I also work, there are many multimodal data available where you see text, audio, video, image, everything together. So, and how do we build a spatio-temporal model using GNN? That's also a nice challenge out there for you. So thank you very much for giving your time. I'll leave 10 minutes for question and answer. So I'd like to quote George Box, like, essentially all models are wrong, but some are useful. Hopefully ours, you find it useful. And if you want this slide, you can just scan it using your like Google search button, and it will land you to the paper and the slide. Thank you very much for joining. It's actually almost late here, so yeah, I finished almost on time. Yeah, thank you.
Thank you very much. Very wonderful presentation. So we have time for Q&A. If you have questions, feel free to unmute yourself or type in the chat.
Oh, I
Our
just saw my
audience,
video
don't be
was turned
shy.
off. I don't know why. Yeah. Oh, you couldn't see me. Okay, that's better actually. I was doing a lot of handwork, so it's fine.
Jordan has a
Oh,
question.
okay. Jordan, please.
Yeah, maybe I can
Yeah.
start. Yeah, really good
Yeah.
talk, very interesting. So you're using the GPD loss function here, and
Mm.
for the generalized period distribution, the support of the distribution function is dependent on your value of the shape parameter psi. And I noticed that you've got that as an output from your graph convolutional neural network. I wanted to ask, how do you go about actually training your neural network using sort of cross-validation techniques? Because
So
if you've
for
got,
the beta 1 and beta 2?
no, sorry, for your shape parameter. If you can,
For
could
the
you,
shape parameter?
yeah.
Yeah. Let me just go to that slide. Yes. Yes. Can you see my screen? Is it visible?
Yeah.
Yes, yes.
Okay. 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 You are telling about this, right?
Yeah, so your shape parameter is a function of I. So
Yeah.
yeah, so if you have a negative shape parameter here, then you've got an upper bound for your threshold excesses, which means that doing any
Yes.
sort of cross-validation is a bit of a nightmare, because you could potentially predict out of sample a scenario where the data that you have in a holdout set is above the predicted endpoint. So that makes sort of gradient-based optimization a bit of a nightmare.
Yes,
Is
yes,
that
yes,
a problem you think
we used actually an optimizer, yeah, out there.
Okay.
We particularly use BFSGS, I think. Yeah.
Okay. I'd love to chat with you more
Mm.
about it. I actually said we tried to use these sort of models to do a similar task when I was at Cal.
Mhm.
I couldn't do it, and
Okay.
we gave up on it.
Oh,
So I'd love to hear more about the technical details offline, I think.
yeah, so I think this part was done like with using, we first tried with using different gradient descent approaches, and finally we could figure out some solution actually. I need to check my code now, but we could figure out how to do it actually. Yeah, we
Okay.
also saw that problem coming initially.
That's
Yeah.
very exciting for me. That's
Mm.
okay.
Yeah.
I'll send you a copy.
And we have a very nicely written code, so I can share you that link. Also has the nice code. Yeah, it's a very
Fantastic.
well
Thank you.
documented one.
Great.
Yeah.
I can ask. So I just
Yeah.
wonder, in your loss function, Does the POT loss get dominated by the MSE loss? Because sometimes there's not a lot of extremes.
Yeah,
So I want.
yeah, for this sort of data, POTL loss, the opposite happens actually. It dominates more. Okay, so for if you have a data which has very minimal number of extremes, then this sort of idea may not be as effective as it should be. So we also tried to check it for Bangalore data. I don't know, have you been to Bangalore? Let's say Bangalore is another city in India which is less polluted, like let's say. So let's say if you try it on Melbourne data, then there will be only a few extremes out there. So that won't be highly effective, given then your data loss will be dominating. It will have the beta 1 will come for close to 1 for that, and beta 2 will goes to 0. So for this sort of data, beta 2 can have a higher value sometimes. Yes.
Thank you so much.
So I have a question on
Oh, hi.
I may have hi I may have missed the beginning of your talk. I wonder
Oh.
if there's some established method for learning the graph, like which nodes have edges. Yeah, I wonder if there's some a method
Yeah,
or
yeah, I actually presented a list of method. If you can see my screen, when starting the talk, I actually presented all these methods inside. I think you probably missed this part, right? Yeah.
yeah. So it seems to me that the selection of edges is a discrete optimization problem. So
Yes.
all these methods they can address this problem.
So not all the methods can do that. Particularly MONet, RelationNet, they studied those edges actually. So some of the methods are only dependent on the nodes and the attributes. So whatever attributes you have, and you kind of think like it's a static graph in the sense of the nodes and edges are same. So remain same over a period of time. So there are some particular graph structure like RelationNet or program as graphs though. So the graphs explosion methods, they actually can help you with the discrete edges problem. Okay, so there are methods out there designed recently that can help. Okay.
Okay. May I also ask how does your method scale with the number of edges per node having?
So in terms of number of nodes, okay, so we actually note the
In terms of a number of
yeah,
edges per node, sorry.
yeah how it scales, actually here the scalability is basically not an issue because of the graph convolution. So we use graph convolution, so where we have, if we have even very large number of edges also, here it's not fully connected network, right? So the number of parameters is always less. Instead of running a fully connected, let's say, convolution network or recurrent neural network, you have to connect all the nodes. Here the weight sharing happens. So even if there are too many edges, the number of parameters will be relatively low, so that will be optimized, so the time complexity will be lower as compared to any standard in a CNN structure.
Okay, thank you.
Thank you so much, Jian.
Maybe I have a general question about the extremes. So when you were fitting the GPD models, I think on one of the graph you were choosing like tau equals to 60%.
Yes.
Mm-hmm.
So yeah, so which one? Okay, I was showing you for Alipur data. Yeah, Alipur data, yeah, which comes here, this one. Yeah.
Mm-hmm. Yeah, I'm
Yeah.
wondering how sensitive like the results are depending on the choice of tau.
Choice of tau. Yeah, so that's a reviewer question. Yes. We saw it in two ways. Okay, one way we showed it actually was initially in the paper we showed it by we choose the tau based on NAC threshold. So whatever NAC threshold for Delhi's locations are given, we took that. But of course, reviewers has nice questions. Then what do we do it actually? We choose the threshold based on MEP. Okay, so mean excess plot. So they asked us to try with mean excess plot and try to work with that. And then we kind of figured out like it's still working for this sort of data, because this data has too many extremes. So that was the beauty of this data. So you will feel like it's a kind of like a gold mine for working on spatiotemporal deep learning. So we actually archived also this data, like just like putting it on GitHub. So for our data, MEP, even we put the results for MEP also. If we find out the threshold based on MEP, then mean excess plot, then how the plots look like, it was very close enough. It's not very much deviating from the based on the tau given by NACS.
Yeah, thank you for the insights. It's always a tricky task
Yeah,
choosing the threshold. Thank
choosing
you.
the threshold. Yeah. For this sort of problem, actually, we are blessed. We have a NAC threshold, so it's easy to work with them if you want. Or perhaps MEP is a heuristic approach, so works sometimes well.
Thank you.
Mm.
Does anyone have a last question from our audience? If not, I think that's it for today. And if you have additional questions for Tanujit, please feel free to email him.
Yes,
And I'm sure
anytime.
he
And
will.
if you pass by Abu Dhabi, then please let me know. I'll be happy to host you here. Okay.
And we will be posting announcement for our next seminar soon. So please keep an eye on your inbox and our website for some update. So thank you all for joining us today. We are looking forward to seeing you all in our next seminar. Bye bye.
Thank you so much. Bye
Bye-bye.
bye.
Thank you.